Okay, Assalamualaikum and a very good morning to all of you. How are you today?
I'm good.
Fine, doctor.
Okay, great. All right. So as usual, we're gonna start our class with Kitab Al-Fatihah. أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله رب العالمين الرحمن الرحيم مالك يوم الدين إياك نعبد وإياك نستعين اهدنا الصراط المستقيم صراط الذين أنعمت عليهم غير المغضوب عليهم ولا الضالين آمين. All right, guys, it's quite heavy rain here at Johor Bahru. And how about your place? Some of you have texted me personally, said that your internet line is so bad due to the really bad flood at your area. Okay, how about you guys? How about your location? Azimuddin, same here in Kelantan, doctor. Where you live in Kelantan, Azimuddin? KB, yes. But really bad place in Kelantan is Kuala Krai, Gua Musang, and so on, right? And anybody here live in Pahang? It's really bad there in Pahang. Okay, Nurul Irfan, how about Pahang right now? Where do you live in Pahang? Kuantan or where?
Rompin.
Rompin, how about Rompin? Not so bad. Because the bad area in Pahang is Raub and I think Bentong as well, right? Lipis, yes. Okay, stay safe, guys. We have two bad situation here. The first one is COVID-19 is still not ending yet. It's really bad in Malaysia right now. A lot of infections daily reported. And then the second one, we have a really bad flood at Pahang and at east coast of Peninsular Malaysia as well as Johor. All right. So for those, anybody here stay in Kluang? Johorian in my class stay at Kluang? No. How about my student there at Saudi Arabia? What is the situation there in Saudi Arabia? Hot or cold or what? Oh, still sleeping, I guess. All right, guys, as you know, for this week, we're gonna learn about high performance liquid chromatography, or we call it as HPLC. It's a really popular instrument, all right, especially in the industries as well as the oil and gas industries, right? It is one of the chromatographic methods, all right. And what are the components of the HPLC system, all right? The basic thing is we have a stationary phase and what phase? Stationary phase and
mobile.
What is the second one? Stationary phase and mobile phase, right? So we have a solvent for a mobile phase, and we have Hplc column, a pack of material that being packed into a column that we call as Hplc column. And then we have pump to move the mobile phase, right? And then to introduce a sample into the system, we need to have the injector, right? We need to have injector or auto sampler for the sample manager. And then we have the detector. As I told you, that is a normal one for the instrument. We have the detectors for every analytical instrument, All right. And then we have the computer data system to translate the detection into a chromatogram. And then last one, we have waste, right? This is the schematic diagram of the Hplc that we need to know, right? Let me annotate somewhere here, right? This is the basic thing of Hplc that we need to know. We have a Hplc column as a stationary phase, right? Right, this one is stationary phase. Oh, really bad, my pen. All right. And then we have the solvent as the mobile phase. All right. Right, this is a schematic diagram that you need to know about the Hplc. Right, what means by performance in the word Hplc? Performance means enhanced efficiency and resolution by the use of small diameter 2 to 5 micrometer stationary phase particles, right? That's why we call high performance liquid chromatography. And the liquid is pressurized to several hundred psi for efficient flow rate. And the most used liquid chromatography method nowadays. So we no longer use just liquid chromatography because the instrument have been upgraded into high performance liquid chromatography. So liquid chromatography no longer, we don't use that anymore. So we use high performance liquid chromatography. What means by performance? The column, right? The stationary phase, all right, being enhanced with a small diameter 2 to 5 micrometer particles inside the column, all right? So now we use Hplc, no longer LC, all right? So overview about Hplc. The first one is form of column chromatography. Pumps a sample mixture or analyte in a solvent. Okay, we need to pump sample mixture or analyte and occur at high temperature. Occur at high pressure. Mobile phase are usually solvent. The stationary phase is column with chromatographic packing material. The carrier gas is helium gas and able to separate and identify compounds that can dissolve in liquid. Right, so the basic principles of the Hplc depends on the interaction of sample analytes with the stationary phase and the mobile phase to effect a separation. It is a basic concept of chromatography. Also applied in Hplc, of course. All right. So we have several types of Hplc. The normal phase Hplc. We have the reverse phase Hplc, right? Also, we have a size exclusion Hplc and ion exchange Hplc. This is how the analyte interact with the stationary phase, right? We learned before this. All right. For the normal phase Hplc, this method separates analyte on the basis of polarity. So NP Hplc use polar stationary phase and non-polar mobile phase. Right. Therefore, the stationary phase is usually silica, and a typical mobile phase are hexane, methylene chloride, chloroform, diethyl ether, and mixture of these solvents, right? And polar samples are thus retained on the polar surface of the column packing longer than less polar materials. Remember, polar love polar. So polar samples, polar analytes love polar stationary phase. All right. So also we have a reverse phase Hplc. Why it's called reverse phase? Because the stationary phase used now is non-polar. It's hydrophobic in nature. All right. And the mobile phase is a polar liquid. So reverse. All right. Normal Hplc we use polar stationary phase and non-polar mobile phase. Now for the reverse phase Hplc, we use a non-polar stationary phase and a polar mobile phase. It works on the principle of hydrophobic interactions. Hence, the more non-polar the material is, the longer it will be retained. Polar love polar, non-polar love non-polar. Polar analytes love polar stationary phase, and non-polar analytes love non-polar stationary phase. Right. Okay, this is how the polar and non-polar stationary phase looks like. Okay. Right. The normal phase chromatography, the stationary phase is polar. Mobile phase, non-polar. The column, similar. Okay. Internal diameter of 4.6 micrometer, length with 150 to 250 micrometer. Millimeter, sorry. So movement of molecule, non-polar molecule travel through the column more quickly in the normal phase chromatography. For the reverse phase, the polar molecule travel through the column more quickly. All right. So the basic principle of Hplc. The first one is size exclusion Hplc. The column is filled with material having precisely controlled pore size, and the particles are separated according to its to their molecule size. Larger molecules are rapidly washed through the column. Smaller molecules penetrate inside the pores of the packing particles and elute later. This is how the size exclusion Hplc works. So the large molecule will be rapidly washed out. Why? Because in the column we have material that have a small pore. What is pores? In Malay we call liang or lubang-lubang halus lah. All right, the small pores all across in the particle inside the column. So the small molecules will penetrate inside the pores of the packing particles and elute later than the large molecules, right? So this is the basic principle of size exclusion Hplc. So what about the ion exchange Hplc? So the stationary phase has an ionically charged surface of opposite charge to the sample ions, because we need to trap. Okay, for example, if we need to differentiate the negatively charged ions inside the sample, so we need to have a positively charged surface on the inside the stationary phase, inside the column. Okay, it's normal, right? Positive interact with negative. All right. This technique is used almost exclusively with ionic or ionizable samples. The stronger the charge on the sample, the stronger it will be attracted to the ionic surface, and thus the longer it will take to elute. Okay, I will ask this example. We have negatively charged ion analyte inside the sample, and we have a positively charged surface particles inside the column. All right. So in the mixture of analytes, we have a large portion of negatively charged ions and a small, portion of positively charged ions. Right. That we need to analyze. Right. This is just for example. So inside the column, when we pump the sample inside the Hplc system, which of the ions, negative or positive, will elute faster? Anybody? We have two charge of ions inside the sample, and we have positively charged surface inside a stationary phase column. So, which ion will elute faster? Anybody?
Negative.
Why negative elute faster? Inside the column, we have a lot of particle with positively charged. Okay. And in our sample, okay. Oh, really bad. How to undo this one? But in the sample, we have a negative and positive charge, right? right? So inside the stationary phase, we have a positively charged surface, okay, packed material inside a column. So we put an ionic solution, combination of positive and negative charge of ions. So which one will elute first? Will elute faster? Negative or positive?
Negative.
Why negative elute faster? You remember what means by elute? Elute means when we introduce a sample into the column, into the stationary phase, the compounds that elute first, that being passed through the stationary phase first, is the compound that do not interact, do not have any interest to interact with the stationary phase. So of course, the one that elute faster is a positively charged, because positive do not interact with the positive, right? It is different with polar and non-polar. This one is ion exchange Hplc. We use ionic charge of compounds inside the column. So the opposite charge will be attract on the surface of the particles inside the column. So the same charge will elute faster. In my question just now, I asked that in our stationary phase right now, we have a pack of material with a positively charged, and we put a solution with a combination of negative and positive charge, right? So which one will elute faster? Of course, the positive charge ion compounds. Understood?
Yes.
Right, because of course positive does not interact with positive. It is sunnatullah, right? It is the nature that God create, that positive charge will attract with negative charge. Woman will attract with man, right? And it is really not normal if men have interest with men. Okay, right? That is not normal. So the sunnatullah, okay, the nature, right? The God create is negative will interact with positive. Positive will interact with negative, right? That is a basic principle of ion exchange Hplc. If we have a pack of material with positive charge in the column, if we put a solution that have negative and positive charge ion, of course the positive will elute faster and negative will interact with the positive charge surface inside the column, right? Right, it's different with the concept of polar and non-polar. That is about the compounds, all right? That is about the molecule itself, not the charge, all right? Polar or non-polar. So in the polar molecules have also positive and negative charge. That's why if we introduce a polar compound, it will interact each other, all right? Because there are charge in the on the molecule. But non-polar doesn't have any charge inside the molecules, all right? The electrons and protons are all stable, all right? Well distributed in the molecule. So there are no charge in the molecules. But if there are polar molecules, meaning that electron and proton is distribute opposite to each other, right? That's why if you put polar compounds, it will interact to each other, right? In this case, it is charge, ionic charge. It's different, right? All right, the stronger the charge on the sample, the stronger it will be attracted to the ionic surface, and thus the longer it will be take to elute, all right? The mobile phase is an aqueous buffer where both pH and ionic strength are used to control elution time. Okay, remember in the ion exchange Hplc, the mobile phase is an aqueous buffer. Sorry, all right. Right, this is the instrumentation of Hplc. All right, like the first slide that I have shown you. This is the basic diagram for the Hplc instrumentation. You need to understand. I don't want to use the word memorize, because I don't want you to memorize, just memorize all the things, but you understand the thing. Of course, you need to be sure that sorry, what happened? We need to have a stationary phase and a mobile phase, right? And some problem with my pen. Never mind. Okay, and then we need to have a pump. Sorry, I need to remove this. Okay, right. We need to have a pump. Okay, so we have a Hplc solvent as a mobile phase. We have pump and injector. There, in the injector, the sample will be introduced and mixed with the solvent, and then being transferred into the column, the stationary phase, right? And then there will be the detector. So the first who elute from the column will be detected. The second one will be detected. The third and so on will be detected, and then will be transformed into the chromatogram in the data acquisition. And after that, the sample waste will be collected here, right? As shown in the schematic diagram, we call this as a schematic diagram in figure above. Hplc instrumentation includes a pump, injector, column, detector, and integrator or acquisition and display system. The heart of the system is the column where separation occurs. This is the heart of the instrument, the column, the stationary phase. Is, for example, we have Hplc with a brand of Shimatsu here in UTM in our lab, right? What is this? What is this? The bottles on top of the instrument. What is that? What inside the bottle?
Solvent.
Yes, solvent, right? And what is this bottle?
Vials.
What? Yes, waste bottle. Don't forget the waste bottle. After the analysis, we need to collect the waste, right? All right, here we have the solvent. This one is different. We have the solvent on top of the instrument, and waste bottle is we put underneath the table. All right. We have a degasser, we have pump, we have detector, sample injector, and Hplc column. Here is the column, very small one. Okay. And then this is a computer system, all right? The normal computer that will, the data in the form of chromatogram will be shown here. Okay. So the solvent reservoir, okay, the container of the solvent is pressurized. We need to pressurize the mobile phase. We use organic solvent in a normal phase chromatography, and we use organic solvent water combination in reverse phase chromatography. For example, methanol water and water acetonitrile. This is in reverse phase. And then mobile phase must be filtered using 0.45 micron membrane filters and degassed by sparging, remove the dissolved gases, vacuuming, remove bubbles, and sonicating. Right? The most important things in the instrument is we need to remove the what? I have told in the spectroscopy instrument. Also, we need to be careful with the sample. We need to remove what? We need to remove all the suspended solids, particle inside the sample, because it will damage the instrument. So we need to filter the samples to make sure that there will be no suspended solids, all right, inside the sample. We need to have a really clear sample solution, because if we do not introduce a really clear from a suspended solid, the sample that really clear from all the suspended solid set sample will damage our instruments, because it will be clogged inside the tube, because the tubes are very small. Okay, will clog inside the tubes and also will damage the column itself. So number one is we need to filter to remove all the suspended solids, right? It need to be filtered. And then number two, okay, this is number one. Number two, it need to be degas. We need to remove all the dissolved gas, right? Remember, in any solution in water, we have a dissolved gas, right? Dissolved oxygen normally, all right? And we need to put inert gas to remove all the oxygen, because oxygen will affect our reading. So we need to remove all the dissolved gas, right? And also by instead of using an inert gas, we also use vacuum to remove bubbles using a vacuum system. And we also have sonicating. Okay, we remove the bubbles, remove the dissolved gas inside the sample using a vibration, a really low frequency vibration using sonicator, right? We sonicate the sample, right? So we have two precaution before we introduce our samples to Hplc. Number one, we need to filter using 0.45 micron membrane filters, and number two, we need to degas. We need to remove all the dissolved gas, especially oxygen inside the sample, right? So this is micro vacuum degasser, right? Right. As the solvents pass through the vacuum tubes, any dissolved gas in the solvents permeates through the membrane into the vacuum container. Okay, this is where this is the bottle on top of the instrument. Okay, and then this is the tube. Okay, and here we have a vacuum degasser, right? We have the push valve and pump head and so on here. As the solvent passes through the vacuum tubes, any dissolved gas in the solvent permeates through the membranes into the vacuum container. The solvent will be almost completely degassed when leaving the outlets of the micro vacuum degasser, right? So it is built-in in the instrument. The vacuum system is built-in the instrument, so that when the solvent being pumped into the instrument, it will be degassed first, right? And what about the columns? Okay, the columns for Hplc is normally stainless steel or glass tubing, right, with a pressure of lower than 600 psi, and the typical length are 3 to 25 centimeter, all right, and the inside diameter of 0.5 to 5 millimeter. The stationary phase, the packing material inside in the column by held in the column by porous discs at column ends, and packing materials, normally silica, alumina, porous polymer, or ion exchange resins. What is resins? Anybody can tell me what it means by resins? Anybody?
Sticky, flammable, organic substance.
Sticky?
Flammable, organic substance.
Can we call plastic? Resins, polymer, it's quite the same species. It's from plastic material, right? All right. Okay. And columns allow mobile gas flow of a few milliliter per minute, and that volumes are kept small. What is that volume? Remember what happened in our chromatogram? The first peak to be appear, right? We doesn't count this thing, right? Because it is the first compound that leaves the or the solvent that leaves the columns, the saturation phase, the dead volume, right? So the dead volume are kept small, okay, so that it will not interrupt with our compound speed, right? And to increase lifetime of column, a guard column or pre-column is often used. So we have a pre-column, all right? We have a pre-column or a guard column to protect, to increase the lifetime of our column, all right? Because it's really expensive to buy a column. I've bought one column for my experiments. It's cost about 3,000, right? I will show you. Wait for a while. How the columns look like. All right, I will stop sharing this slide. Okay. Look at this. This is the box, right? Hplc column, right? We have now we are deboxing the Hplc column live with me, right? Normally we have a cover like this. Okay, cover like this, and we remove the cover, and now we unboxing the column. So we have the manual, all right? And now we can see the column. This is the column, right? You can see it. Unboxing time with me, all right? So what type of column is this? Okay, this is C18 column. Okay, read it, for reverse phase Hplc, right? Made in, can you see that? Made in where? USA, all right? So if you can make column really good, made in Malaysia, please do that, okay? This is Agilent brand. Agilent is a USA brand, okay? We also have Agilent Hplc instruments here, right? Okay. Unboxing time is now finished, okay? Now we continue to our class, okay? Hplc column. How much? About 3,000. Okay. Okay, now finish unboxing time. Where are we just now? Column, right? All right, type of column, we have a pre-column, an auxiliary column that precedes the analytical column. The guard column protects the analytical column by removing particulate matter and contaminants. Again, inside a guard column, the contaminants or the particulate matters need to be removed. So we have several protection mode inside the Hplc. And now we have the analytical column. Okay, the length normally 10 to 25 centimeter, right? With the inside diameter 4.6 or 5 millimeter. The packing particle size 3, 5, or 10 micrometer. The short 3 cm column packed with particles lower than 3 micrometer are becoming popular because of faster separation. Why? The short columns give faster separation? Anybody can answer this? Why the short columns, 3 cm column, right, packed with lower than 3 micrometer are becoming popular with faster separation. Why fast? Why it faster than the normal size of column? Anybody? Open your mic and answer. Hello? Am I speaking to myself? Or I have students now? Why?
Less resistant.
Why?
Less resistant. Because the short one have a short distance, so it can separate in small.
Yes. Because it's short, right? Lesser distance for the compounds to travel inside the column, right? And then it will be separate faster, right? The result will be faster because it is shorter, right? That's all, right? Okay. But of course, it's quite expensive, right? Because the materials are carefully designed inside the packing. The packing particle size also, have been designed to be very accurate for the testing. All right, instrumentation. Okay, just ignore the tissues here. We have syringe. Why we have syringe? To inject the sample, all right? Stainless steel or glass tubing, all right? A stationary phase, all right? And then we have type of column that have been taught previously in previous slide, okay? Okay, now we learn about a pump. To deliver the mobile phase across the column up to 6,000 psi, all right, at 3 milliliter per minute with minimum pulse and continuously and reproducibly 2% and under isocratic or gradient illusion. Isocratic or gradient illusion. Remember this magic word. Okay. Isocratic or gradient illusion. All right. A reciprocating pump with a pulse dampener is used for a smoother flow. A syringe can also be used with limited capacity. Now, remember this word, right? And we will go for this word after this. So this is a pump, right, to deliver for the desired pressure with a minimum pulse and continuously and reproducibly and under isocratic or gradient illusion. This is a magic word, isocratic or gradient illusion. Right? This is the instrumentation. Right. For the injector, it is used to inject the sample into the mobile phase, of course. And type of sample injection techniques are auto-sampler or valve injector. For the auto-sampler, it can inject a large number of samples. A small vial with a septum are placed in a tray. Okay, needle penetrates septum and withdraws the sample, and valve introduce the sample into a column. Similar with the AAS, we have also the auto-sampler in a chromatography instrument, especially for Hplc, because it's quite a routine work to do. You need to inject sample inside the instrument again and again, so that an auto-sampler will do all of the jobs. So what we only need to do is to put our sample inside separate vials, okay, with numbers. Then we program it in the computer, so the auto-sampler will do the job for us. So when we prepare the sample inside the auto-sampler, we program it in the computer. Tray number 1, for example, vial number 1, for example, is what? Number 2 is what? And then we just can have our lunch. We can play football while waiting for the instruments to analyze the sample, right? We also can watch movies to wait for the instruments to analyze our sample. Okay, this is how the auto sampler looks like. We have a lot of sample vial holes here with a specific number. So we only need to put here and program it in the computer. Just put the information of the sample inside the computer. So we know what kind of sample that the instrument analyzes. Okay, instrumentation. This is the valve injector. It is used to introduce sample quantitatively onto column without interrupting the mobile phase flow. Sampling loop consists of various loop sizes for different volumes. When placed in load position, sample is loaded into an external fixed volume loop at an atmospheric pressure, and when rotated to inject position, loop become part of the eluent flow stream, and the sample is carried to the column. Okay, this is how the valve injector looks like. This is where we inject the sample into the loop. Okay. Now for the detector, we have several types of detector for Hplc. We have a UV visible, we have a fluorescence, we have a refractive index, or a diode array detector, right? Remember, we have a UV, fluorescent, refractive index, a universal detector, and also we have a diode array detector based on UV visible principle and most common. So the diode array detector is the most common Hplc type. Okay. The choice of detectors is determined by the solute type, the solute concentration, detector sensitivity, linear range, compatibility with the solvent, illusion mode, and also we have a coupled detector. Okay, we have a coupled detector, meaning that after the it been detected by our diode array, it will be also again detect using mass spectrophotometer, mass spectrometry. So also we have LC and MR. We have nucleus magnetic resonance, right? It's still a high performance, but we don't mention HP in front of it, all right? Because it's too long, basically. We know it is liquid chromatography, but we have another detector that being used. We have two detectors, the normal one and MS or NMR, right? So it is quite an expensive instrument. So if we use LCMS, we could know when compared with the library of the compounds, we could know what type of compounds that available inside our sample. For example, in the library set, the compounds our sample are, for example, epigenin inside the. Normally, we have epigenin in the a plant extract, so it's a complex molecule that we need to we need to isolate. So if we detect quite similar with the mass spectrometry inside the instrument library, so the library will the instrument will read the library and compare, and it will show that it will suggest that our peak is from this compound. This is for example. Right, so diode array detectors. Okay, advantage of Hplc. Okay, it is high sensitivity use of various detectors. The range is part per million to part per trillion. Okay, we have a UV conductivity detector, fluorescence, electrochemical detector, MS, and so on. Compared to TLC, we have learned previously TLC, the simple thin layer chromatography. Hplc is quick and efficient. Okay, that is the most important criteria for the analytical instrument: quick and efficient. Usage of pump to force the mobile phase through a solid adsorbent material, and we get high resolution and accuracy. All right, so the result will be accurate and automated because it can be performed with a minimal supervision. The instrument will do it for us. So we only need to analyze the result that have been produced by an instrument. So it's also wide analytical applications for pesticide analysis, organic and inorganic materials, food components, toxins, vitamins, and so on. All right, now we learn about the illusion profile, the illusion mode. How do you want to strip out the retain analytes? Remember, we have the retain analyte inside the column. We have the one who move faster, slower, the one who want to attract with the stationary phase. So I ask you to remember the word, right? The first one is isocratic illusion. We have two types, isocratic or gradient. So in isocratic illusion, the mobile phase composition, okay, the ratio of polar to non-polar illusion is constant in a chromatographic run. Okay. Remember, for the mobile phase, okay, we need to some type of Hplc. We need to combine the non-polar and polar mobile phase. Let us back again to the slide that I said about the combination of the yes. Where is it? Okay, now in the reverse phase, okay, we have the mobile phase, a polar liquid and a mixture of water and methanol and acetonitrile, for example, right? It needs to be mixed. So in the isocratic illusion, okay, for the mobile phase program, remember we have a program for the pump to bring in the mobile phase inside the instrument, okay? So in the isocratic illusion, the program for the mobile phase being pumped into the Hplc, right? The ratio of polar to non-polar illusion is constant from beginning until end, right? Constant. For example, okay. For example, we need to mix ratio of polar to non-polar is 1 to 3, right? 1 polar to 3 non-polar illusion as a ratio. So it will be constant from beginning until end. But for the second program, gradient illusion, the mobile phase composition change during a run. The strength of an illusion is increased by varying the ratio of solvent, for example, polar versus non-polar solvents, to obtain a better separation in a shorter time. How? Okay, the instrument itself will mix the mobile phase, polar and non-polar, with a different ratio. We ourselves program in the instrument. So, for example, in the first 5 minutes, the mobile phase is the ratio of mobile phase is 1 to 3, polar and non-polar. And after 5 minutes, it changed to 2 polar and 3 non-polar. And after 10 minutes, it will change to 3 to 1, 3 polar, 1 non-polar. That is for example. So when we program, the mixture of the mobile phase ratio will change according to our program. So it's not similar from beginning until end, right? Am I correct? Understand? Understood?
Yes.
All right. That is different between isocratic illusion and gradient illusion. So for isocratic, it is maintained. The ratio of the mobile phase, polar and non-polar, is maintained from beginning until end. But for gradient illusion, it will be programmed to change with time. Okay, the ratio of polar to non-polar mobile phase that pump into the instrument together with the sample is changed during time. What is the purpose? It is to obtain a better separation in a shorter time. Okay. So solvent with the increasing polarity, okay, the most non-polar is hexane, and then a little bit polar heptane, and then petroleum ether, and then cyclohexane, and then trichloroethane, and then toluene, and then dichloromethane, and then chloroform, then ethyl ether, ethyl acetate, acetone, and propanol, ethanol, and the most polar solvents is water, right? The most polar solvent in the earth. Okay, so this is the how isocratic illusion and gradient illusion being programmed. So for isocratic, it's just this solvent from the beginning until end. But for the gradient illusion, we have a solvent A and solvent B, right? Because if we need to mix with ratio, for example, for this isocratic illusion, we do not have to have two pumps, right? Because we mix together at the beginning until end the same ratio, so we just put inside the a solvent reservoir. But for gradient illusion, we need to program the ratio, right? So we have to need we need to have two pumps, because the ratio of the solvent mixture will change with time when we program into the instrument. So we need to have two pumps and two type of solvent. So it will be changed by itself after we program. So it's no longer similar from the first minute until end. The ratio are not similar. Okay, it will be changed, right? So that is the difference between isocratic illusion and gradient illusion. So we have an example of the usage of the solvent program, isocratic or gradient. The first one is mixture of 6 components have very different partitions coefficients, hence a very different illusion times when using isocratic illusion A, B, and C. All right, so okay, again I read, a mixture of 6 components have a very different partition coefficient, hence very different illusion time. Okay, meaning that the peak appear differently. So when using isocratic illusion, mobile phase is 90% of water and 10% of methanol, right? We have optimum for 1 and 2, but excessive time for 5 and 6 is too far here. If we wait for the illusion, okay, we have first peak, and then we have second peak, and then we have to wait, and there the third peak come out, and then the fourth peak come out, and then we need to wait a really long time for the fifth peak and sixth peak to come out. All right, for the second one, B, we have a ratio of 80% of water and 15% of methanol. Okay, is optimum for 5 and 6, but 1 and 2 and 3 and 4 are unresolved. See, 1 and 2 we cannot differentiate, we cannot separate the peaks, right? But 5 and 6 now is already good, it's come out early, no need to wait until this time, right? But now the problem is 1 and 2 and 3 and 4 here and here, the peaks are not separated. So here it comes, we have to program the mobile phase, right? But this is not, the third one also not so good, all right? We are not programming the gradient yet. This is still isocratic. We use 80% of water and 20% of methanol, but optimum for 3 and 4, the peak already separated well, and 5 and 6, the time of the illusion already improved, but the problem is for 1 and 2, it's still not well separated. So we need to program the mobile phase into a gradient illusion, right? When using isocratic illusion, we have a not so well distributed peak. We need to have a longer illusion time for the last peak. But after we program, okay, the composition of the solvent is changed continuously or in a series of steps too, right? We have a really nice peak here, okay? Well separated, and the elution times is not so long, right? Right, now polarity versus elution time for normal phase then reverse phase, all right? For normal phase, the low polarity mobile phase, okay? And then we have CBA, right? Compound will come up through the time. And then if we use reverse phase, of course, A will come first because it's reverse now, okay? B and C, right? With the medium polarity mobile phase, right? And we have a CBA with, you know, not, the peak is not, the peak is quite close to each other. And then, mobile phase for the reverse phase is like this, right? So example of Hplc separation of various compounds. So this is as example, right? This is a real chromatogram. We have naphthalene, acinaphthene, fluorine, phenanthrene, anthracene, fluorantine, and so on. We have a lot of compounds here, right? In the polyaromatic separation of polyaromatic hydrocarbons inside the canola oil, right? This example of polyaromatic hydrocarbons inside the canola oil, right? This is a separation conditions. Sample preparation, we use SPE, solid phase extraction. Later we will learn the sample preparation for a chromatography technique, all right? And sample matrix, of course, we have canola oil, spiked with PAH, and then we have SPE tube cartridge, and then we have condition. What kind of condition? 10 ml of acetone dry. We have a sample addition, we have a elution program, we have a eluate post treatment, okay, and so on. This is how the separation condition used to analyze. To have a really nice peaks here. We have a well separated peaks, and the elution time is also not so long, right, to each other. So we need to program with gradient elution. We need to play with the ratio of the mobile phase, right? This is the program, the optimum program to analyze the canola oil. So again, for every sample, we need to develop a method. If we don't have a standard method to analyze the sample, for example, for canola oil, of course, we already have the standard methods. A lot of compounds now, we already have the standard method. But in case we are now, in the future, you are given a task to analyze a new compounds, right? You need to develop a method by yourself, right? Play with the ratio of the mobile phase, right? So that at the end you have a very good, well distributed peaks, all right, with the high resolution and a good chromatogram criteria that I have taught before this in the previous class in the introduction to the chromatography. We have a criteria of the chromatograms that we have also formula to count, right? To have a really good solvent program and so on. And also we need to have a not so long elution time. Okay, we need to, we don't need to wait for a long time for the peak to come out, okay, for just one peak. So we need to shorten the time. So we need to play with the solvent programs, type of column, sample preparation, and so on, so that we have a really nice method with a good chromatograms resolution and elution time, right? This is chromatogram of Hplc separation of proteins, all right? Example of ribonuclease A, cytochrome C, holotransferrin, and myoglobulin, all right? And this is the separation conditions, the standard method, right? For drugs, right? Heroin, oxycodone, codeine, morphine, right? This is the standard method. So that's all for Hplc. The most important part in the HPLC that you need to understand is the first one is normal phase and reverse phase. What is the difference? And then the solvent program, isocratic and gradient illusion. That is the famous question that being asked in the final exam normally, right? But it's okay. We'll do revision after this. All right, that is about HPLC. For now, I need all of you to watch the videos that I have searched regarding the HPLC. All right, like this. Okay. The first is I will put the link of the video inside the e-learning. Okay. We have two videos. The first one is about sorry, this is the first one. The first one is about 7 minutes, and then the second one is about 30 minutes, right? You have to make sure that you watch this video by today during this class, okay? And because it's quite, you know, the sound is not so good when I played during this class, during this synchronous class. What I'm gonna do is I will put these two videos in the e-learning, and then you need to watch by today, right? And then Irfan, are you there? Our class rep, Irfan, are you there?
Yes. Yes.
And our
Yeah.
deputy class rep is Sabrina, right? Am I correct?
Yes, doctor.
Okay, so you have to make sure that all of you watch the video today. That is your task for both of you. Okay? Make sure you watch it by today, no later than today, because you will forget after this. Am I clear, both of you? Okay.
Okay.
So have all of you scanned the attendance? All right, I will share the attendance again. Please, for those who not scanned the attendance yet. And then I will dismiss the class for now after you scan the attendance, okay? And I will upload, oh no, I will put the link of the video inside the e-learning, and you need to make sure that you have to watch it by today. Irfan and Sabrina, please make sure all your friends watch the video by today, and I will ask in the group later, okay? And that's all for our synchronous class, okay? Make sure you watch the videos after this, okay? Thank you and Assalamualaikum.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you.